Hi everyone, I just wanted to make a quick video on the review for chapter 6 topics and our kind of other topics that we've talked about in this course. So I want to concentrate on kind of these first two bullet points here. So derivatives and integrals of exponential functions, e to the x, ln of x, inverse trig functions, and derivatives of inverse functions. We've reviewed a little bit of average value already, so I don't want to spend too much time on that. But you can go back to the video that I originally made for those topics as well. So I'm just going to go through kind of a quick example of each type of problem. The derivative of an e to the x function. Remember, when we do a derivative, we want to use the chain rule if there is anything in the exponent. So our derivative of 2e to the 7x would be 2 times e to the 7x, and then multiplied by whatever the derivative of the exponent would be. So times 7. So our g prime here, if we wanted to clean that up a little bit, would be 14e to the 7x. And you could use that in conjunction again with any like power rule, or not power rule, chain rule, product rule, quotient rule. If we want to go the other way, so if we want to find an antiderivative of an e to the x function, if there is anything in the e exponent, generally that's what we'd want to set equal to our u value. So I'm going to set u equal to 5x squared. That's going to tell me du is 10x dx, and dx would be du over 10x. So doing my substitution, that's going to give me 2x e to the u, and then times du over 10x. My x's are going to cancel out. That 2 over 10 can become a coefficient on the outside, so I'm going to write that as 1/5 times the integral of e to the u du. And the antiderivative of e to the u is just e to the u. So that's going to become 1/5 e to the u. If this is an indefinite integral, we want to remember the plus c. And then we would just want to substitute back in whatever our u was. So 1/5 e to the 5x squared, and then plus c. So right after we talked about exponential functions of e to the x, we talked about the natural log functions. We talked about how to find the derivative of those, and then calculating antiderivatives of the form that's going to give us something of an ln of x type function. So if we want to find the derivative of this ln of 4x to the third, remember that our general form of our derivative is, if it's an ln on the outside, it's going to be 1 over whatever's on the inside. But then we need to also chain rule that by multiplying by the derivative of whatever's on the inside. So derivative of 4x to the third is going to be 12x squared, and we would want to clean that up. So that's going to give me 12x squared over 4x cubed, which should leave me with just a 3 in the numerator, and I think just an x in the denominator. So my h prime here would be 3 over x. And we did talk about like expanding functions if there was like a fraction on the inside with the natural log on the outside. So don't forget about those types of problems. You could encounter those as well. For example, 4, this is a 1 over something type of a deal here. If we tried to use u substitution here and set u equal to 2x plus 5, that should give us something in the form of 1 over x, which we know with the antiderivative, that would be the natural log function. So I'm going to set my u to be whatever's in the denominator here. So my du is going to be 2 dx, and my dx is going to be 1/2 du. So if I do my substitution, 1 over u, and then times 1/2 du, I'm going to pull that 1/2 out as a constant. And this is in the form of the integral of 1 over u, which we know is the ln of, well, in this case, it'll be u with, again, don't forget your absolute value. So that's going to be 1/2 times the natural log of the absolute value of u, which we would say is 2x plus 5. And then since we are indefinite here, don't forget your plus c. Okay, so then there were some rules of derivatives and antiderivatives of exponential type functions that I think I gave you guys a video to review. So if you need to go back and look at that video again, you can also do that. But just kind of a quick review of what those rules were. If I have a base of something like a number to anything, it could be a variable expression, it could be a trig expression. The rule was to say my f prime here would be keep whatever that expression is the same, multiply by the derivative of the exponent, and then we want to multiply that by the natural log of whatever the base is. So my base here is 3, so that'd be multiplied by the natural log of 3. And you could rearrange these terms if you wanted to, so you can make it kind of look a little bit nicer, or you could leave it in that form as well. If we wanted to find the antiderivative of an exponential function with the base that's some numerical value, if there is something else in the exponent other than just x, we probably are going to need to use a u substitution here again. So I'm going to set my u equal to whatever is in that exponent. So 5x. du is going to be 5 dx, and that means dx is going to be 1/5 du. So doing my substitution, that's going to give me a 4 to a u, and then times 1/5 du. Again, I can take that 1/5 out as a constant. And this is in the form of a base of a number value to an exponent, which is in the form that I need it to be in to take the antiderivative. So our antiderivative rule said, well, first I'm going to bring down that 1/5 constant. And then I'm going to do 1 over the natural log of whatever the base was. So base of 4 here, so 1 over the natural log of 4. And then multiply that by whatever this expression is, so whatever the base is to the exponent. Don't forget that we want our plus c since this is indefinite. And then I would want to go back and substitute in whatever my u was, and we can make this into one fraction. So I can write that as 1 over 5 times the natural log of 4 times 4 to the 5x power, substituting back in that u value, plus c. Sometimes they'll have it written as one fraction, so you might see it written as 4 to the 5x over whatever the denominator is. And don't forget that sometimes you can, or it will actually put that 5 as an exponent on the 4. So you might see it written as the natural log of 4 to the 5th. And then plus c. Okay, so since we're on the subject, well, now we're going to go on the topic of inverses. So the first type of inverse that we talked about was just a general inverse function. So we're given some function f, and we know that g is the inverse of this function f, and we want to know what the derivative of g evaluated at the x value of 1 is. So the first thing we need to do is we need to figure out what g of 1 is, because remember that the formula here would tell us that g prime of 1 is going to be equal to 1 over f prime of g of 1. So I need to know what this g of 1 value is, and I can do that by taking my original f of x value and setting it equal to whatever this x value is, because I want to know what x value would make that true for the inverse function. So I want to find g of 1 first. And I'm going to take this x value of 1, and I'm going to set it equal to this f of x function. And I need to figure out what x value is going to make this equation true. Well, if I kind of eyeball this and see, okay, well, I have a 1 over here. I need it equal to 1. These two values must be 0. So lucky for us, sine of 0 is 0, and then 2 times 0 is also 0. So since this would be sine of 0 plus 2 times 0 equal, or plus 1, that must mean that g of 1 must equal 0. And this is going to be a helpful value because now I can go ahead and substitute it into this formula. So my g prime of 1 is going to be 1 over f prime of 0. But then I need to know what f prime is so that I can actually calculate this value. So the next thing I want to find is what is f prime of x. All derivative of sine is cosine. Derivative of 2x is going to be 2. Derivative of 1 would be 0. So if I evaluate f prime of 0 here, cosine of 0 plus 2 is going to give me 1 plus 2, which should be 3. So that would mean that when I plug that back in over here, g prime of 1 would be 1/3. And then the last type of inverse functions that we talked about were the inverse trig functions. So don't forget those formulas that we talked about, like the 1 over the square root of 1 minus x squared and all those. You do definitely want to know those. So finding derivatives of those, that's where the formulas are going to come into play. So remember that arctan is really the same thing as saying the inverse tangent. So what I'm looking to do here is I'm looking to take the derivative of the inverse tangent of cosine of x. So my initial setup here is going to be to use the inverse tangent formula, which is 1 over 1 plus x squared. That's the derivative of the inverse tangent. But remember that when there's something on the inside of the parentheses, that's what we're treating as x. And if it is not just x, we also need to use the chain rule. So my derivative here would be 1 over 1 plus, again, it's not going to be x squared. It's going to be cosine of x squared, because that's what's on the inside of the parentheses over here with the inverse tangent. But then I also need to chain rule this. So I need to also get the derivative of cosine. So that's going to be times negative sine of x. So my cleaned up version of my derivative would be my f prime is going to be equal to negative sine of x over 1 plus the quantity of cosine of x squared. And you could also write this as cosine squared of x. That would